Okay, so this week I want to talk about recursion. We're going to be using a ton of recursion through this course because we'll be implementing our interpreter for our languages using recursion. And we're trying to learn some functional programming techniques. Recursion is a fundamental aspect of that. So let's look at a simple recursive function like the factorial function, right? So it should take in an integer, and it's going to return an integer. And what do we do? Well, if n is equal to, let's say, less than or equal to 1, then we return 1, else return n times factorial and applied to n minus 1. Right, so this is where the recursion is happening. It's any time we have the function call itself. Now, one of the key aspects of recursion is you have to know, does this actually end, right? Will this call ever finally finish? And that's when it reaches what's called a base case. So the base case here is if n is less than or equal to 1. And since we're passing in an integer, which can be any whole number, negative or positive, we know that anytime it gets to a negative number, or anytime if it's positive, right, what's going to happen? We call factorial on n minus 1. This number keeps on getting smaller and smaller and smaller until it eventually hits 1. If we initially fed it a negative number, then it would automatically get caught by this base case. So regardless, this computation will finish. It's easy to modify this into a situation where it won't finish, right? If I do, say, factorial of n plus 1, then this is a perfectly well-defined Scala function, but it will never end. It'll go on forever, right? Because as we just keep on feeding this, adding a new factorial function onto our stack, and it just keeps getting bigger. So what happens here as we execute this? Well, we have our first call. Let's do, say, factorial of 4. What happens? Our first factorial here, right, it goes through the base case stuff, and then it hits this recursive function. And so it needs to call factorial of 3, which likewise runs through the base case calculations, and then it comes across the subcall to factorial 2. The base case, and then the call to factorial of 1, which finally hits the base case, and then returns 1, right? So it passes 1 back to our previous factorial of 2. And what does 2 do to it? Well, it multiplies n times whatever number it got back. So and in this case, n is 2. So it multiplies 1 by 2, 2 times 1, and then passes that back. What does factorial 3 do with the return on its recursive call? It takes 3 and multiplies it by whatever it got there, so it gets 3 times 2. And this gets passed back to our base factorial call, which then multiplies 4 times the leftover 6 that was passed back. And we get 24, right? So this is what's going on under the hood. This whole process here is called the stack. What's really happening is we get something called an activation record. For each one of these function calls. An activation record typically keeps track of all of the local information that we might need for our function. So it'll say that n is equal to, say, 4 for the base one, and maybe there's some other variables going on, like maybe there's an x that's a string with, let's say, capital I. And the most important thing, which is the return call, or return address, which points to whatever function called it before, usually some activation record lower down on the stack. So this would be, say, our main function that called factorial 4 for the first time. And so when factorial 4 ends up calling factorial 3, it just writes a new activation record on top of the previous one with now n is equal to 3. Let's say x is, again, capital I. And the return address is now the factorial of 4. And then factorial 3, it adds, it calls factorial of, factorial of 3 calls factorial of 2, and its return address is factorial of 3. Typically it's pointing to the exact location in that factorial, right? What is that line of code where I'm going to return to after I've finished all the calculations that I need to in factorial 2. N equals 2. We still have our dummy variable I. And then we have fact of 1, which has the return address of fact of 2. And so this is our stack, right? And as we add on, as we do these subcalls, they just keep growing the stack upwards. And the activation record on the very top tells us what is our current function that we're running. And then as soon as factorial 1 finishes, it removes its activation record and then returns to wherever this return address was, right? So that's the location at the arrow right here. And likewise, factorial 2 will finish doing whatever calculations it needs and then return to its return address. And then we keep on doing this until we get back down to our original call of factorial 4, which then returns 24 to whatever had called it, like our main function. So this is how recursion is handled by your computer or by the compiler or interpreter, is that we basically have this stack that grows that tells us in fact where the function calls are coming from and where we should return to. Now if we say have too many of these calls and our stack gets too big, there's typically a limit on it, then we end up with what's called a stack overflow, of which the famous website is named. Right? Our stack runneth over in activation records.